Hi everyone, in this video we are going to discuss about the excentral triangle and its relationship with the original triangle. We will prove that the incenter of the original triangle is the orthocenter of the excentral triangle, which would mean that the original triangle is actually the pedal triangle of the excentral triangle. So let's first try to understand what is an excentral triangle. Well, an excentral triangle is the triangle which is formed by connecting the excenters of a triangle. For example, we have a triangle ABC and we are going to draw the excenters of this triangle. I have already created a video where I have described what an excircle is and how to figure out the length of the Exradii and everything. I have shared the link in the description. Feel free to watch that video. Now in this video, we are again going to draw the excenters. Now how do we draw the excenters? Well, we have to draw the angle bisectors, which will also create the incenter as well as the excenter. Now to draw the excenter, we have to extend each of the sides of the triangle. So let me first extend the sides of this triangle. Here, as you can see, I have extended the side AB up to B sub 1, and then I have extended the side CB up to B sub 2, and similarly I have extended the side BC up to C sub 1 and AC up to C sub 2, and also I have extended the side CA up to A sub 1 and BA up to A sub 2. Next, I am going to draw the bisector for the interior angle A, which is near the vertex A. Let's suppose that that angle bisector is AD, and also I have extended it so that when we draw the bisector of the exterior angles, they will meet at a point and that will become our first excenter. Next, I am going to draw the bisector of the interior angle B, and let's assume BE is that bisector, and also I have extended it so that we can draw the excenters. And finally, I am going to draw the bisector of the interior angle C. Let's assume CF is that bisector, and also I have extended it so that we can draw the excenter number 3. Next, I am going to draw the bisector of the exterior angle DBB sub 1. And let's assume that this bisector intersects our extended AD at the point I sub 1. Similarly, I am going to draw the bisector of the exterior angle DCC sub 2, and let's assume that the bisector is CI sub 1. It will meet at the same point where the previous two bisectors intersected. And let's assume that point to be I sub 1, and that is actually the center of our first excircle, meaning the excircle which is opposite to the vertex A. This is the center of that excircle. Next, I am going to draw the bisector of the exterior angle ECC sub 1, and let's assume that it intersects BE, the extended BE, at the point I sub 2, and that is actually the center of the second excircle. And also I am going to draw the bisector of the exterior angle EA sub 2, and let's assume that it is AI sub 2. That's the line segment which bisects the exterior angle EA sub 2. So the second excenter is at I sub 2, that is the center of the excircle which is opposite to the vertex B. Now let's focus on to the third portion here. So next I am going to draw the bisector of the exterior angle FA sub 1, and let's assume that it intersects the extended bisector CF at the point I sub 3. That is the center of our third excircle. That excircle is opposite to the vertex C, and I sub 3 is going to be the center of that excircle. And finally, I am going to draw the bisector of the exterior angle FBB sub 2, and let's assume that it is BI sub 3. That's the line segment which bisects that exterior angle FBB sub 2. So I sub 3 is the center of our third excircle. Now let's move on to the proofs. Now if you look at this triangle I sub 1, I sub 2 and I sub 3, this triangle is actually called the excentral triangle, because this triangle is formed by connecting the excenters of the original triangle. This triangle is called the excentral triangle. In this video, we are going to find out each of the angles of this excentral triangle, and also we are going to prove that each of the extended interior angle bisectors of the original triangle, they are nothing but altitude of the excentral triangle. For example, if I look at I sub 2B, it is actually perpendicular on I sub 1, I sub 3. Similarly, I sub 1A is actually perpendicular on I sub 2, I sub 3, that line segment. And also if you look at I sub 3C, that is also perpendicular on the line segment I sub 1, I sub 2. And we are going to prove that. since AD bisects the A angle, then each of the smaller angles there would be equal in size and each of them will be half of A. I have denoted that with a green arc there. So please assume that each of those angles, like the angle BAD and the angle DAC, they are actually equal in size. Each of them will be equal to half of A because AD is the bisector of the angle A. Similarly, since BE is the bisector of the angle B, then each of the smaller angles will also be equal in size and each of them will be equal to half of B, and I have denoted that with a pink arc there. So each of the smaller angles like CBI and IBA, each of those smaller angles is equal to half of B, and also since CF is the bisector of the angle C, each of the smaller angles there like the angle BCF and the angle FCA, they will also be equal in size and each of them will be equal to half of C, and I have indicated that with a red arc there. So each of those angles are equal in size and they are half of the main angle of the original triangle. And here on the left hand side, top and bottom, I have made some notes here. Let's assume that the side length of the original triangle AB is equal to C units and BC is equal to A units and AC is equal to B units, and similarly angle BAC is denoted by uppercase A radian, angle ABC is denoted by uppercase B, and angle BCA is denoted by uppercase C radian. And also down below I have noted that angle BAI is also equal to angle IAC, which is also equal to half of A. Similarly, angle ABI is equal to angle IBC, which is equal to half of B, and also angle BCI is equal to angle ICA, which is also equal to half of C. I hope things are clear up to this point. Next, we are going to prove that I sub 2B is perpendicular on I sub 1, I sub 3. That means the angle I sub 2, B, I sub 1 will be equal to 90 degree or pi over 2. Now, if you think about it, B, I sub 2, it is the bisector of the angle B. So what would be the size of the angle I sub 2 BD? That angle will be half of B. And what is the size of the angle DBB sub 1? That is equal to pi minus B because it's the exterior angle, so that would be pi minus B. Then what would be the size of the angle DBI sub 1? That will be equal to half of that because BI sub 1 is the bisector there. So that would be half of this angle, half of pi minus B, and that is equal to pi over 2 minus B over 2. Now from here, if you think about it, angle I sub 2 B I sub 1 is actually sum of two angles. One of them would be I sub 2 BD and the other one is actually DB I sub 1. Now we have found the values of these two angles, so I'm going to simply replace the values here. The value of the angle I sub 2 BD is actually half of B, and then the value of this other angle, which is the angle DB I sub 1, that is actually 90 degree minus half of B, and if you carefully look at it, this is nothing but pi over 2 because half of B, positive and negative, they will cancel each other, so this is going to give us pi over 2. So you can clearly see that the angle I sub 2 B I sub 1, that is actually a 90 degree angle. That means I sub 2 B is actually perpendicular on the line I sub 1 I sub 3. Now if you are thinking why I sub 1 I sub 3 is a straight line, well, using the same technique we can also prove that the angle I sub 2 B I sub 3, that is also a 90 degree angle. So if we have two 90 degree angles next to each other, then guess what? I sub 1 I sub 3, this line segment will be a straight line. So that is why you can see that each of the sides of this excentral triangle is actually a straight line. And using the same technique, we can also prove that I sub 1A is perpendicular to I sub 2 I sub 3, that side of the excentral triangle. And also we can prove that I sub 3C is perpendicular to I sub 1 I sub 2, this side of the excentral triangle. And now let me highlight this. So from here we can see that each of these original internal angle bisectors, the extended ones, right, they are actually altitudes of the excentral triangle. So then the point of intersection of the three interior angle bisectors of the original triangle which intersected at point I, it is the same point through which the altitudes of the excentral triangle are passing through, right? So that point, being an incenter of the original triangle, it is acting as an orthocenter of the excentral triangle because the same point is also the point of intersection of the altitudes of the excentral triangle. This is a very interesting concept. Please look at the diagram again, that I sub 1a is perpendicular to I sub 2 I sub 3 side, then I sub 2b is perpendicular to I sub 1 I sub 3 that side, and then I sub 3c is perpendicular to I sub 1 I sub 2 this side. So each of those yellow dotted lines, they were originally the interior angle bisector of our original triangle ABC, and now it is looking like they are also the altitudes for this excentral triangle because we have proved that they are perpendicular onto the opposite side. So then the incenter of the original triangle is actually the orthocenter of the excentral triangle. This is the first proof that we wanted to do in this video, and now in the second part we are going to see how to calculate the size of each of the angles of this excentral triangle. I mean each of the interior angles of this excentral triangle, and here the excentral triangle is nothing but the triangle I sub 1 I sub 2 I sub 3. So we are going to find each of those angles, like for example angle I sub 1 I sub 2 I sub 3, and the angle I sub 2 I sub 3 I sub 1, and the angle I sub 3 I sub 1 I sub 2. So let's see how we can find out those angles. And here we are going to see some interesting geometry, so take a look at it carefully. Now in this diagram, if you look at the quadrilateral BICI sub 1, this quadrilateral has a pair of opposite angles which are actually 90 degree each. That means their sum will be 180 degree. And let me show you with a yellow highlighting here that this angle right here, which is the angle IBI sub 1, that is a 90 degree angle. And similarly, if you look at the angle ICI sub 1, that is also a 90 degree angle. That means if we look at this quadrilateral, which is BICI sub 1, in this quadrilateral we have a pair of opposite angles whose sum is actually 180 degree. That means this is a cyclic quadrilateral. And because it is a cyclic quadrilateral, we can now use some interesting property of circle. Now let's take BI as one of the chords, right? So if BI is the chord, then if you carefully see that BI is actually subtending two angles onto the circle here. One angle would be BCI, that is one angle, and the other angle would be BI sub 1I. Think about it. The same chord BI is extending an angle which is BCI and also angle BI sub 1I. I am making a note here on the left hand side, and because BICI sub 1, this quadrilateral is a cyclic quadrilateral, the angle subtended by the same chord will be equal. That means these two angles will be equal. Now what is the value of BCI, that angle? Well, that is actually half of C. That means this angle right here, this will also be half of C right here. Think about it. And similarly, if we take CI as the other chord, now let's take CI as the other chord, right? Now CI is also subtending two angles. One of them would be CBI and the other angle would be CI sub 1I. So the angle CBI and the angle CI sub 1I, they will also be equal. Now what is the size of the angle CBI? Well, that is actually half of B. That means this other angle right here, this angle will also be half of B right here. Now let's look at the quadrilateral which is CIAI sub 2. So next we are going to talk about the quadrilateral CIAI sub 2. In that quadrilateral, again using the similar technique, we can prove that the two opposite angles which are near the vertex A and C, for example this angle right here which is ICI sub 2, that's a 90 degree angle, because we have already proved that I sub 3C is perpendicular on this side here. So the angle ICI sub 2 is a 90 degree angle, and similarly we have also proved that the angle IAI sub 2, that is also a 90 degree angle. That means each of these angles right here, they are 90 degree angle. Let me highlight that with a red color here. So this angle right here, the angle ICI sub 2, that angle is a 90 degree angle, and similarly the angle IAI sub 2, that is also a 90 degree angle. Think about it. That means in this quadrilateral, the quadrilateral AICI sub 2, in this quadrilateral we have a pair of opposite angles whose sum is 180 degree. That means this is also a cyclic quadrilateral, and because because it is a cyclic quadrilateral, we can imagine Ci to be one of the chords. Now if you look at the chord Ci is subtending two angles there, right? One angle would be CAI. So let me make a note on the left hand side. So the angle CAI and the angle Ci sub 2I, those two angles will be equal because the same chord subtends equal size angle on the circle. And since we have proved that this quadrilateral is a cyclic quadrilateral, Ci can be imagined as a chord of that circle, and the same chord is subtending these two angles, so those two angles will be equal. Now what is the size of the angle CAI? Well, that is actually half of A. That means this angle, the angle Ci sub 2I, will also be half of A. Alright, now let's take the chord AI, and if we take AI as the other chord of that circle, then AI also subtending two angles there. One angle would be ACI and the other angle would be AI sub 2I. Let me make a note on the left hand side. So the angle ACI and the angle AI sub 2I, they will also be equal in size because both of them are subtended by the chord AI. So then what is the size of the angle ACI? Well, that is actually half of C. That means the angle AI sub 2I, that will also be equal to half of C. So let me make a note of that there. So this will also be equal to half of C right here. Now let's look at the quadrilateral AIBI sub 3. That quadrilateral is also a cyclic quadrilateral, because if you look at the angle IAI sub 3, that is a 90-degree angle, and similarly the angle IBI sub 3, that is also a 90-degree angle. Let me show it over here. So we are talking about these two angles right here. I am highlighting with light green color here. The angle IBI sub 3 and the angle IAI sub 3, those two angles are 90-degree angles each. That means their sum would be 180 degrees. So now if you look at that quadrilateral, which is AIBI sub 3, in that quadrilateral we have a pair of opposite angles whose sum is 180 degree. That means this quadrilateral is also a cyclic quadrilateral. And then we can use AI as one of the chords. Now if you think about AI, now AI being a chord of a circle, it is subtending two angles there. One of them would be AI sub 3I and the other angle would be ABI. So let me make a note of it here. I am making a note in red color in the lower part of the screen here. Angle AI sub 3I and the angle ABI, those two angles will also be equal because they are subtended by the same chord AI. Now what is the size of the angle ABI? Well, that is actually half of B. That means the angle AI sub 3I, that will also be half of B. So let me denote that right here. So this is also half of B. And similarly, if we take BI as the chord, then BI is also subtending two angles there. One of them would be BI sub 3I and the other one will be BAI. So those two angles will also be equal. Now if we say the angle BI sub 3I, so I am making a note here, BI sub 3I and the angle BAI, they will also be equal because they are subtended by the same chord BI. Now what is the size of the angle BAI? Well, that is actually half of A. So then angle BI sub 3I, that will also be equal to half of A. So this angle right here, this will be equal to half of A. And now if you look at each of the angles of this excentral triangle, we have been able to find out the value of each of those angles. Now what are their value? Well, let's make a note here. Let me erase some of my work notes here on the right hand side, and here I'm going to use that space to make my notes for the interior angles of the excentral triangle. So the first angle that we are going to talk about is actually angle I sub 1, I sub 2, I sub 3, that is equal to half of A plus half of C. Now can this be written as 90 degree minus half of B? Because you see our A plus B plus C is equal to 180 degree, and then if we divide both sides by 2, we are going to get half of A plus half of B plus half of C is equal to 90 degree or pi over 2. And from here you can see that half of A plus half of C is equal to 90 degree or pi over 2 minus half of B. So in place of half of A plus half of C, we can write pi over 2 minus half of B. So here I am going to write this is actually equal to pi over 2 minus half of B. And similarly, let's now look at the angle I sub 2, I sub 3, I sub 1. This angle is equal to half of A plus half of B, and this can be written as 90 degree minus half of C. And also let's look at the third angle, which is the angle I sub 3, I sub 1, I sub 2. This is looking like half of b plus half of c, and this can be written as 90 degree minus half of a, and that was the second part of our derivation that we wanted to do in this video. The link of the video that I have shared in the description, in that video you will see I have calculated the length of each of the sides of this excentral triangle, and also I have calculated the distance of each of the excenters from the incenter of the original triangle. All of that derivation has been done in the other video. The link is available in the description. Feel free to watch that video. There you will see how to calculate the length of each side of this excentral triangle. Here in this video we wanted to prove that the incenter of the original triangle is also acting as the orthocenter of the excentral triangle, and in that case you can imagine that we are actually joining the feet of the perpendiculars of the excentral triangle to form the original triangle. So the original triangle ABC is looking like the pedal triangle of the excentral triangle. That's a very interesting concept here, that the excentral triangle is created by bisecting the angles of the original triangle, and now the original triangle seems to be formed by connecting the feet of the perpendiculars of the excentral triangle. So the original triangle ABC seems to be the pedal triangle of the excentral triangle, and the incenter of the original triangle is acting like the orthocenter of the excentral triangle. I hope everything made sense. Thank you for watching. See you in the next video.